Hey everyone, so these are the solutions to Worksheet 10.1. We're going to be talking about angles as a warm-up to getting into trigonometry here. So in number one, we're given an angle that's expressed in terms of degrees, minutes, and seconds, and we're asked to convert it to a decimal approximation of this, rounding to 3 decimal places. So let's think about what we're being given here. So 42 degrees, 3 minutes, and 11 seconds. If we were to write this in terms of all of these being parts of degrees. So, for example, 42 degrees is straightforward. That's just already in degrees. Now, the 3 minutes. So there are 60 minutes in 1 degree. So 3 minutes would be 3 divided by 60 degrees. Now, with the seconds, so we know that there's 60 seconds in a minute, 60 minutes in a degree, and this gives us 11 divided by 60 squared, or 3,600 degrees. So let's work about getting a decimal approximation for these, for the minutes and for the seconds. So 3 divided by 60, that's the same as 1 over 20, so that's going to give us a decimal approximation of 0.05 degrees. And then the 11 over 3,600, it's not going to, it's a non-terminating decimal, so we would have to go ahead and round this off a little bit. This is going to give us 0.0030555 repeating degrees. So in terms of these minutes and seconds, this is what they would be in terms of degrees. So to sum all this up, if we're converting into decimal degrees, we've got 42 degrees plus 3/60ths of a degree plus 11 3600ths of a degree. So we add all of these together, and this is going to give us approximately, if we round to 3 decimal places, 42.053 degrees. So that would be our answer there. Okay, so for number 2, we're getting into the idea of the 2 different ways we can express a degree measure, either in degrees or in radians. And here we're given angles in degrees and asked to convert to radian measure, keeping them exact and using the pi in terms of pi. So let's do these. So 240 degrees. Now we want to convert 240 into radians. And the way we do that is we multiply by the conversion factor, and we consider, well, there are pi radians in 180 degrees. So if we multiply by pi divided by 180. So again, these 2 quantities are the same. Pi radians is the same quantity as 180 degrees. So it's almost like multiplying by 1, except we're going to be converting our units here. So the degree units will cancel out, and we're left with 240 over 180 times pi. Now sometimes it's a little bit tricky to get the simplified rational form of the exact answer in radians. So what I like to do is think about the actual fraction, in this case 240 over 180, and try to simplify it. Now in this case, 240 over 180 will actually simplify to 4 over 3 times pi. That's a perfectly fine way of writing it. Alternately, we may see it written as 4 pi divided by 3. Either of these are perfectly acceptable and correct. So let's do the same thing here for 135. So we'll take 135 degrees, and we're going to multiply it by the conversion factor of pi divided by 180 degrees. So this gives us, the degree units cancel out, and it gives us 135 over 180 times pi. And we can see that the 135 over 180 reduces to 3/4 times pi. And again, we could see this written as 3 pi divided by 4, but it doesn't matter. Okay, so sometimes I'll get asked how to simplify this. Well, one way you could do it is, if you have your calculator, you could take the 135 divided by 180, and you'd see that this would actually come out to 0.75, which you should recognize as 3/4. If it comes out to be a decimal approximation you're not familiar with, you could always, on your TI calculators, if you hit the math button, the first option is frac, and if you hit enter, having this decimal number in the empty field already, it'll convert that into a simplified fraction form. So the math and then option 1 frac will do that for you. So that's one way to do it if you can use your calculators. All right, so negative 270, we'll do one more of these. So this is a negative angle. We want to make sure we don't lose that. So negative 270. And again, we're still going to just multiply this by pi divided by 180 degrees. So it's going to be negative 270 over 180 times pi. This reduces to negative 3/2 times pi, or negative 3 pi over 2. Okay, so that's how we convert from degrees to radians. Now, in number 3, we're asked to convert from radians into degrees. Now, this is going to probably be helpful at first if it's been a while since you've had a trig class or never had one before, because degree measures are just a little more intuitive and easier to visualize. So sometimes as you're getting used to radian measure, it helps to convert that angle from radians into degrees so you can visualize the angle of rotation a little bit more easily. So this is a definitely helpful exercise to do. So let's take the negative 2/3 pi, and we're going to go ahead and convert this. So we've got negative 2 pi over 3. Now, similar to the way we converted last time, we're going to use that conversion factor. Now, in this case, we want degrees, so we're going to have the degree part of that conversion factor up top, and then the pi radians in the bottom. So again, quantity of 180 degrees and pi radians is the exact same quantity, just a different unit associated with it. So one thing we'll notice here is that we've got a factor of pi in the top and the bottom, so we can basically lose those. That'll simplify to 1. And then we're left with minus 2/3 times 180 degrees. And if we multiply this out, we end up with a negative 120 degrees. So that's basically the process for all of these. So we'll kind of motor through these. So we've got 7 pi over 6 times 180 degrees over pi. Again, the pi's will cancel out, and we're left with 7/6 times 180 degrees. And if we multiply that up, we get 210. So 210 is a 210 degrees is an equivalent angle measure with 7 pi over 6. And then lastly, 11 pi over 6, we take the radian measure. Now, all of these have pi in them, but sometimes you'll get radian measures that don't have pi in it, but the process is the same. If you're given an angle in radian measure, just go ahead and if you want to convert it to degrees, multiply it by 180 degrees divided by pi. And again, in this case, if we do this, we get 11/6 times 180 degrees, which gives us 330 degrees. Okay, so we've hopefully gotten a little more comfortable in terms of converting between the two types of degree measures we're going to be using. Now, in number 4, we're asked to sort of visualize and sketch these angles and then find ways of classifying them. So first, we're asked to graph the oriented angle in standard position, meaning that the vertex, the point of rotation, is the center of rotation is the origin, and then classify each angle to where its terminal side lies. So we want to know basically which quadrant it falls in, or if it lands on one of the axes. We'd want to be able to recognize that. So let's go ahead and just let's get a little set of axes going here. So we've got our y-axis, and we've got our x-axis. So negative 240 degrees. Let's go ahead and sketch that real quick. So we start on the positive x-axis, and now we're going to rotate negative 240 degrees. So let's see how that works. So rotating negatively means we're going to rotate we're going to rotate clockwise. So if we do that, we're going to go, that's negative 90, and then we can go, that's another 90, so negative 180. So we still have another 60 degrees to go in the negative direction, which is going to put us right here. So that would represent our angle of rotation. Now in this particular case, we are sitting in the second quadrant. So we could go ahead and say that this angle right here is a quadrant 2 angle because of where it falls. Okay, so now we're asked to give two coterminal angles, a positive and a negative one. So coterminal just means that the angles start in the same place and they have the same terminal side. We don't worry about which direction it spins or how many times it spins around. As long as they start and end in the same spot, they're considered coterminal. So let's do the positive coterminal angle first. Now we're in degrees here, so we'll call this theta sub c, and I'll put a little plus right there to indicate it's positive. Now the way we're going to do this is we can just start with our initial angle, in this case 240 degrees. And we can get a coterminal angle just by adding or subtracting multiples of 360 to get there. Now in this particular case, if we want a positive, we should be able to get there just by adding 360 degrees. And if we do that, we get 120 degrees. So notice that if we wanted to graph 120, we'd start at our initial side and we'd rotate positively 120. So both of these angles have the same initial side and the same terminal side. Okay, so if we want to get the negative coterminal angle, let's go ahead and we'll call this theta sub c minus. And if we take 240 degrees, negative 240 degrees, we can get a negative coterminal just by subtracting 360. And if we do that, we'll get 600 degrees. So again, if we wanted to visualize this, we start on the positive x-axis. We're going to start rotating around. So there's negative 360, and we've still got a negative 240 to go. So all three of these angles, negative 240, 120, and negative 600, all have the same initial and terminal sides, so they're all considered coterminal. Okay, so let's move on to the next one. And we've got 11 pi over 6. Again, if you can visualize this in radians, great. Eventually you should be able to, but for now, let's just go ahead and convert this into degrees to maybe help visualize. And we know from the previous problem that 11 pi over 6 is the same as 330 degrees. And while we're at it, let's go ahead and sketch this angle. So we'll draw our axes here. And then let's sketch this 330 degrees. So we're rotating positively 330 degrees. So that's 30 degrees shy of one full rotation. So that's going to put us here just 30 degrees away from completing a full rotation. Now in terms of the quadrant here, we have fallen into the fourth quadrant, so we know that this is a quadrant 4 angle. And now we can go about finding our coterminals. So if we start with our positive coterminal angle, now we're going to want to do, our final answer should be in radians. However you want to do it is up to you. If you want to go ahead and, since we've got 330 degrees, find the coterminal in degrees and then convert to radians, that's fine. I'm going to do it all in radians from the start here. So we're going to take our 11 pi over 6, and we can get a positive coterminal by adding one full rotation. So instead of adding 360, I'll do 2 pi, since we're in radians here. And to add these two together, we'll take 11 pi over 6. We'll convert 2 pi into a fraction with a denominator of 6, which is going to give us 12 pi over 6. And when we add these together, we'll just get 23 pi divided by 6. So that would be a coterminal positive angle. And now to do our negative coterminal, we would take 11 pi over 6. And in this particular case, if we were to subtract one full rotation, that would give us a negative coterminal. So that would be 11 pi divided by 6 minus 12 pi over 6. And that gives us just negative pi divided by 6. So if we were to sketch these two coterminal angles, 23 pi over 6 would look something like this. We rotate in the positive direction. There's 2 pi, and then we go another 11 pi over 6. Whereas the negative coterminal angle, we start on our initial side, and we're just going to rotate negative pi over 6, and that'll put us in the same spot. Okay, so not too bad. Let's do part C. So theta is equal to 750 degrees. So we'll start by getting our axes set up here. And one of the things we're going to run into here is that now we've got an angle, a positive angle that's greater than 360. So we're going to be doing multiple rotations here in order to get there. So let's try and visualize this. So we'll keep track of what's going on. So we're going to start with 750 over here. And as we go through, we're going to rotate. And so now we've gone 360 degrees. So if we subtract 360, that's going to give us, what, 390 degrees left. So we've got 390 left. So let's go. So we keep going around, and we do another 360. So if we subtract the 360, now what we have left is we've got 30 degrees. So now we've got 30 degrees left, which is going to put us right here. So there's our angle of rotation. So 750 involved 2 full rotations, then 30 degrees left over. And notice that this puts us in the first quadrant. So this is a quadrant 1 angle. And now we could go about finding coterminals. In this case, if we're paying attention, the positive coterminal angle is going to be very easy. We've actually got several of them already. Notice that 390 and 30 degrees would both be considered examples of coterminal angles here. But if we wanted to follow the pattern that we've been doing, we'd just take the initial angle, 750, and we would add, this is just a guaranteed coterminal angle for us here, positive one at least. That would give us 1110 degrees. But 390, 30 degrees, both of these would be acceptable answers as well. And then to do a negative coterminal angle, we'd take the 750. Now notice, just subtracting 360 is not going to get us there. We're going to have to back off more than 2 rotations here. So one way to do this is I'm going to subtract 3 rotations from 750, and that should give us a negative one. So I'm going to subtract 360 degrees times 3. So that's going to give us 750 degrees minus 1080 degrees. And that will give us an angle of rotation of negative 330 degrees. And you could draw those, and you could see how they match up. And then the last one for this question is negative 5 pi over 2. Again, just if you're having trouble with this and you want to visualize it in degrees, great. If we converted this, we'd end up with negative 450 degrees. So if we go ahead and we sketch this. Now, one way that you could help start interpreting radian measure, this is negative 5 times pi over 2. Pi over 2 you'll want to remember as a negative, or as a 90 degree angle. So we're rotating negatively 90 degrees 5 times. So if we wanted to, that's one way to think about it. It might be more confusing. But if we think of pi over 2 as a 90, we're going to do 5 rotations of 90 degrees in a negative direction. So this would be negative pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4 pi over 2, negative 5 pi over 2. That's one way it might help to think about it. Now notice we're not in a quadrant here. We're actually on the negative side of the y-axis. So that's how we would classify that, as we're on the y-axis but the negative side. So the negative y-axis. And now we just go about finding our coterminal angles like we've been. The positive one, we're going to take minus 5 pi over 2. Again, just adding 2 pi would not get us there. We're going to have to do 2 rotations. So I'm going to add 2 pi times 2. So this is minus 5 pi over 2 plus 4 pi. We get our common denominator. We've got minus 5 pi over 2 plus 8 pi over 2. And that's going to give us 3 pi over 2. Again, I'm going to draw this one just because it's an important angle. So negative or positive 3 pi over 2 would be pi over 2, 2 pi over 2, 3 pi over 2, 270 degrees. And then our last one here, we're going to get our negative coterminal angle, negative 5 pi over 2. Again, there's plenty of different answers for this. There's an infinite number of answers for this. But if we were to, let's just subtract 2 pi. So that's going to give us minus 5 pi divided by 2 minus 4 pi divided by 2. And that'll give us negative 9 pi over 2. So again, just remember that there are multiple answers you could have come up with for these. There's technically infinite answers I'd mentioned before. So, but those are just some examples how you could find coterminal angles. Okay, so the last problem here is a bit of an application. So we're told that a 3-inch diameter yo-yo spins at an estimated 4,000 revolutions per minute. What is the speed of a point on the outer edge of the yo-yo in inches per minute? So real quick, let's kind of imagine this. So yo-yo, we know we've got a string it's coming down on, and then it's a circular object that's going to be spinning around. So we know that this is, it doesn't matter which direction it's spinning, but we know that it's spinning at a speed of 4,000 revolutions every 1 minute. And we also know that if we were to look at the diameter of this, the distance from edge to edge through the center, that it's a diameter of 3 inches. Okay, so what we're asked to consider is if we just looked at some point on the outer edge of this, what is the speed of it in inches per minute? Now, when we start talking about the speed on the outer edge, and try to relate it to something that we've talked about in this section, hopefully what you should be thinking of is linear velocity. Now, speed is just the absolute value of velocity without direction. But we talked about if we have circular motion and we want to find the speed of something moving around, or the velocity of something moving around in that circle tracing a line, linear velocity is what we want to use. And the formula that we have for linear velocity is it's equal to r times theta divided by t. Again, where r is the radius, theta is the angle in radian mode, and t is just time in whatever unit of time we're using. So if we were to go through and to kind of put these pieces together, one of the first ones we could get is the radius. So the radius of this circle, we're actually given in terms of diameter. So we know that the radius is just half of the diameter of a circle, which in this case means it's going to be 1/2 times 3 inches, or 1.5 inches. So there's our radius. Now the theta and t. Now the theta divided by t might remind you of another formula that we talked about, which was angular velocity. And angular velocity is defined as theta divided by time. It's the speed of the change of the angle. Now, in terms of information that we're given about this, we're told that the angle, or we're going to get 4,000 revolutions in 1 minute. Now, this is going to cue us into the angular velocity because we know that 1 revolution is 360 degrees, or in the case of radians, since we have to be in radian measure here, it's 2 pi radians. So again, we're going to note that theta must be in radians. So this tells us that these 4,000 revolutions are going to be equal to 4,000 times 2 pi, which is going to be equal to 8,000 pi in radians. So that's going to be our theta. That's the number of radians that this yo-yo spins over the course of 1 minute. So let's start to put all of this together. So we know that the linear velocity will be equal to r times theta divided by t. And if we put the pieces that we have so far, we've got 1.5 inches times theta, which is 8,000 pi. And then the time that it takes to do those 8,000 pi is going to be 1 minute. Okay. And if we multiply this out, what we end up is 12,000 pi inches per minute. And that's exactly what we were asked. We wanted to know what the speed is, and it's in inches per minute. Now, to have this make a little more sense, we could approximate this, and this gives us 37,699 inches per minute. So that's the speed of a point on the outer edge of the yo-yo. Now, now it also asks us to consider, could we convert this to miles per hour? So let's do that one next. So miles per hour. There is one bit of information that may not be accessible readily from your brain. You might need to look this up or be given it. But in order to convert to miles per hour, we are going to want to know this. And this is fact that 1 mile is equal to 5,280 feet. So that's really the only piece that we need to get this conversion going on here. So let's convert 12,000 pi inches per minute into miles per hour. So we've got 12,000 pi inches per 1 minute. And this is kind of like in chemistry where you do those stoichiometry problems. You're converting from one pair of units or unit to another. We need to sort of link this up with a bunch of conversion factors. So the first thing I'm going to do is take care of the inches. We want to convert inches to miles. So one way we could do this is to first convert inches to feet. So we know that in 1 foot there are 12 inches. Now what that does is that takes care of the inches unit. And then we want to convert feet into miles. So we know that in 1 mile there are 5,280 feet. So that allows us to get rid of the feet. And now we've converted, if we were to multiply this out, we'd have converted 12,000 pi inches into miles. The other thing we need to do is convert minutes into hours. So we know that we want the hours in the bottom, so there are 60 minutes in 1 hour. So we can cancel out the minutes unit, and now we've got our answer. So we just multiply everything in the top, multiply everything in the bottom, and we'll be good to go. So we've got 12,000 pi times 1 times 1 times 60, all over 1 times 12 times 5,280 times 1. And again, this is the unit up top is now miles, and then the unit in the bottom is hours. So what we end up with here is that V is approximately 35.7 miles per hour. So that's the same speed as the 37,699 inches per minute, just different ways of expressing it. Okay, so that does it for the solutions for this video, and I will see you all in the next one.